All right, welcome back from spring break and into our new and improved online-only method of computer architecture, which is going to be very, very interesting, especially since the next part of this course is the most important piece of information in this entire course. So, the memory system. The memory system, as we will find out soon, is the bottleneck when it comes to performance. So much so that we come up with very complex memory hierarchies in order to improve performance, and we will get speed ups in the realm of 50 to 100 times normal execution. So these are massive factors of speed up due to how slow memory systems are. And from a security standpoint, the fallout of the system we have chosen has incredible security issues. Namely, they are what lead to Meltdown Inspector, Meltdown being the Intel issue that allows basically any attacker to just start reading all the memory on your computer. So, unfortunately, before we can get to Meltdown or the performance, we need to do a lot of background work, and then we can eventually build up to the memory system. A lot of this is not going to be directly applicable to your single cycle processor, so I'm not adding anything onto it. But it is something separate, so you'll have kind of two pathways going at once. But hopefully you learned in this course that that's basically how this course works out. Now, hopefully everyone, in case you're not on right now, everyone should be on Discord. Today I will do a live version of this, but moving forward, since we are going to strictly online only, I will start recording my lecture before class, and then I'll post it on YouTube. And then y'all can watch it, and I'll be logged in during class time to answer some questions. But I won't do this live stream thing again unless I need to. So, any questions before we get going? Any comments, screams?
Gate 2 isn't until the 23rd, right?
Oh yeah, we need to adjust these dates because of the ridiculousness that's going on. What's today?
Today is the 17th.
17th is due in a week.
Oh, so it's due in a week. Oh no, that's fine. Yeah, that's good.
We already delayed it even before the coronavirus got in.
Yeah, so y'all have no excuse.
But the coronavirus has infected my computer and deleted all my homework.
I believe you. Redo it.
Oh, okay.
Excellent. Good talk. All right, so memory system, talk a little bit about it's the bottleneck. So far we've actually discussed two structures about holding data, which is what memory does. One is the register file, which is a little array of storage, and main memory, in this case our data memory, which is a bigger array of storage. We have actually talked about two different types of storage devices. One is the static memory made with logic gates, i.e. this is your SR latch and your flip-flops. The other one that we've talked about is the ROMs, which is where we had a line and then we put a diode on it in order to, I guess, simulate a read-only memory system. Now, when it comes to our memory, we do want to have lots of memory for our processor because when we write a program, we don't want to run out of memory. That's just annoying. Our design, currently, we have 2 to the 16 words of memory. MIPS, which we're not implementing, but if we were doing a 32-bit system, it would have 2 to the 32nd bytes of memory. For those of you who need the conversion, that's about 4 billion bytes, aka 4 gigs of memory. Maybe some, and probably most of us actually nowadays have more RAM than that. x86-64 can have 2 to the 64 bytes of memory, and I forgot what that number was, but it's ridiculous. So what choices do we have in order to implement it? Well, we've done SRAM where we have logic gates, and we could do that. There's something called DRAM, which we haven't quite gotten to, but we'll talk a little bit more about that. We can use our disk or our hard drive if we want to, and if we really want to go old school, I guess we could use paper, but be a little slow. Derek, do you got paper? Derek is gone. All right, am I still connected? Good.
No, I have paper. I had it in full screen. I couldn't get back to the thing to tell it to turn my mic on.
Oh, okay.
I've got so much paper. I'm at my desk. I've got like plethora of paper.
Okay. So it is important to at least talk about the cost of memory and storage. Before we fully analyze this graph, notice on the left that this is a logarithmic scale, aka it goes 1, 10, 100, 1,000, 10,000, et cetera, et cetera. That means if there's a linear line, or a line like you see here, that actually means an exponential decrease in something. And what we're looking at here is the different technologies that come out, flip-flops, integrated circuits, SIMs, DIMMs. Most of us use DIMMs now, hard drives, floppy, SSDs, and flash sticks. If you notice, the price from about good old 55 all the way up to, well, this graph's now a little old, 2015, it's been going down basically exponentially, and this has been essentially the case and is still today, and probably will be for at least another 5 years. But by the way, it's always been at least 5 years in the future that we have a good idea about what we can do. But right now, it just looks like 5 years will still keep this trend going. So yeah, memory is becoming cheaper. So one thing we can do, excuse me, is now that we've talked about being cheap, we'll talk about, unfortunately, one thing that's expensive, and that's called SRAM. And SRAM is the type of memory that we've talked about with our flip-flops and our latches. It has about 5 to 10 nanosecond access, which is pretty fast. The decoders are big, the arrays are big, aka, in other words, it takes up a lot of space, because if you remember your D flip-flop, it was many, many gates in order to get that thing working. And it does cost a lot of money, about $7 per megabyte, so that would make a gigabyte about $7,000. 43 cents for our design, which isn't bad, 28,000 for MIPS, and 123 trillion for x86. Anyone got that? Didn't think so. DRAM.
It's pocket change.
Pocket change. It's the government. We got that lying around. All right. DRAM. The way DRAM actually works is we utilize something called a capacitor, and I know you haven't taken EE too much, but the idea is a capacitor is really, I'll simplify life and just call it a battery. Basically, you charge it and then it discharges, and the idea is the capacitor is going to hold the charge. We're not going to go too much into the design of DRAM, but the idea is that you just utilize a capacitor instead of having the entire circuit diagram that we had earlier with our flip-flop. It does, unfortunately, take a little longer to have access, 100 nanoseconds. But, of course, this begs the question, why build a fast processor that stalls for dozens of cycles on a memory load? Because if you think about this, if it's at 100 nanoseconds, you're at 1 gigahertz, that means each clock cycle is a nanosecond. That means 100 cycles is going to go by before you can get something from memory. Well, anyways, that's what DRAM takes. Still costs a lot of money. It's about $68 per gigabyte. Okay, this slide needs to be updated. It's probably more like $68 for 8 gigabytes. Ends up being less than a penny for our design. What would that be divided by? So about $60-70 for a MIPS, and still, wow, hundreds of billions of dollars for x86, which would not be a good idea. Option 3 is to use disks. Now, this slide uses a spinning disk number. SSDs are faster, but not by as much as you would want. Just take off 2 zeros. So instead of 10 million, it's 100,000. So yes, that means in order to access the hard drive, you have to wait 100,000 to 10 million cycles in order to get memory back. In other words, that load word takes 10,000 cycles where you just sit there and you wait for memory to come back. The joke here is we might as well stop at the Intel 4004. For those of you who don't know, that's the first x86 based processor. Okay, it's not x86, but it's a prequel to x86. Ooh, Maya has joined. Nice. Luckily, the costs are pretty reasonable. 25 cents per gigabyte. It's probably cheaper than that nowadays. $1 for MIPS, $4 billion for x86. Wow, it's still expensive. So, if we want to implement all this memory inside of our address space, these options don't look that great because they all cost a lot. And even, well, they cost a lot, and even the one that's cheap takes forever to actually get something done. Because notice that the cheaper you get per capacity, the longer it takes to access. Okay. So we want a memory system that runs at processor clock speed, 1 nanosecond for our 1 gigahertz processor. We want a memory system that we can afford, maybe 25 to 33% of the total system costs. Options 1 through 3 are way too slow, aka all 3 of those options, because even the SRAM, which is our fastest option, still takes 5 to 10 nanoseconds in order to complete, which means that when we do a load, we are waiting and doing 5 to 10 units of nothing while we wait for memory to come back. Options 1 or 1 through 3 are way too expensive, so we need to come up with a different option. Anyone want to take a guess on what option 4 is going to be?
A combination of all of it?
Nice. You looked ahead, didn't you?
I just vaguely remember a little bit from last year.
Oh, okay, thanks. So, we're going to end up use a little bit of everything, but use it very wisely. So we use a small array of SRAM because small means fast and it also means cheap. So SRAM was the most expensive, but if we use just a little bit of it, it won't be that expensive. And we, since it's the fast part, maybe we can come up with some technique in order to utilize the small, fast, cheap fast SRAM, even though it's a little more expensive, as much as possible. Use a larger amount of DRAM and hope you only have to use it rarely, aka use it as a backup to your small amount. And then for anything really big, go to disk. And of course, never try and buy 2 to the 64 bytes of anything. It'd take decades to format, probably way longer than a decade.
What if you wanted to download the internet? You need that much space.
To download the entire internet? That would easily fit in less than 2 to the 64th. Someone needs to calculate. It's probably less than 2 to the 40th or something. Well, 2 to the 48th. Yeah, 2 to the 64th is something absurd. I forgot the number. I think it has 19 zeros, if I recall correctly. Yeah. Okay, so we're going to use a small array of SRAM for the cache, and the cache is a small piece of memory used to access, that we want to access as often as possible, so it's going to cache main memory or reflect a piece of main memory in hopes that you can go and use the cache instead of main memory. We'll use a larger amount of DRAM for the main memory and then use really a large amount for disk storage for something called virtual memory. And again, don't try and buy 2 to 64 bytes of anything. By the way, today we're going to focus on cache, and we're going to talk about main memory, and it's going to be later on that we're going to talk about virtual memory. So this is the famous memory hierarchy. Wait, do they do the food pyramid anymore? I forgot about that. Anyways.
They do.
They do? Oh, good. So
I think it's slightly reorganized with like a little less grain, but it's been reorganized, but it's the same pyramid.
Okay, good. We still have the pyramid. Excellent. So notice at top the cache, which is small. It has the highest cost. The highest cost, lowest latency, aka it's it's really fast, and it has a high access cost, aka cannot represent most of memory. Of course, main memory is in the middle, where the cost is in the middle, latency is in the middle relative to the other ones, and access is in the middle, while disk storage is the cheapest, takes forever to get to, and you can access whatever you want. So that's mainly the idea here. Now, before I go on, I will mention you probably have heard something called the L1 cache, L2 cache, L3 cache, and I've been seeing the L4 cache. Just think of it as you might have the L1, L2, L3, L4, and then main memory. So the different levels of caches are just how big or what level in the chain of caching that you put it in. And we'll go into a little details about why that's useful later on. But for this course, we're just going to consider having the cache in main memory, because that should depict the idea here. All right. So, do I get to hear someone? Oh. All right. Okay, let me pause for a moment.